SwayamPrabha. Digital India. Educated India.
Welcome to the class of Intelligent Product Design. Today we are going to take our knowledge of the modeling of a control system further by taking up some particular cases of electromechanical systems and their representations. The first one, of course, is the task that we have left from our last lecture, that is the modeling of a DC servo motor, which is so very important. You remember I told you that this now robot, which is having 25 degrees of freedom, which means for every degree of freedom there is a servo motor, and every servo motor is very, very expensive. So you need to design it and you need to procure such servo motors if needed after doing the proper modeling of the system. Now, how do we do this servo motor modeling? What are they are present in it? Well, first part is that we have to understand it has some mechanical part and some electrical part. The electrical part are like you are applying a voltage, and then there must be some resistance involved in the system. There must be some inductance involved, because every motor has some kind of coiling that is there, okay, the electromagnet part of it. So that is there, and then of course this is kind of excited by IF, that is from the field itself, and the rotation of the system is also going to create a back EMF on the system. We have to keep that in our mind, that as the system will rotate there will be a back EMF. Now, these are all electrical part. What is the mechanical part? Well, the servo motor must be rotating some shaft. So, this is that shaft. So, that shaft that is getting rotated at this point, about this point, having an angular velocity omega and with a torque TL, that is the mechanical part of the system. So, now if I try to put all these things in an equation of motion, how would it look like, or the governing equation? The first one is that the torque developed by the motor, how much it is, that torque Tm, it must be proportional to the current that I am applying. So, this Kt is called the armature constant. So, this is armature constants times the current Im. Now, then as this shaft is rotating, then this rotational body is creating a back EMF, that is Em, and that is proportional to the angular velocity. The faster it moves, the more back EMF it generates, nature's own way, which gives a sort of resistance to the process. So, here you have these back EMF constant. So, this we will call it as back EMF constant. Now, since this entire thing is happening through the same armature, so most of the times it is safer to assume that Kb equals to Kt. Now, we need two equations of motion, one for the electrical system, for which we can use the Kirchhoff's law, in which we can say that the EA, the voltage, equals to this inductor part Lm dim dt plus Rm Im, that is this the resistor part, the voltage drop, plus Em, that is the back EMF that is getting generated. So, that gives us the complete picture of the electrical equilibrium of the system. From the mechanical equilibrium, so you have a force balance, that is the torque generated by the motor minus the torque load, if there is a load involved, that must be equal to the inertia force. So, this is the inertia force, and then B d theta dt, that is the damping force. There will be some losses always in a motor. So, thus we are getting two equations of motion of a system. So, I can basically write these two equations first in time domain, and I can also later on write it in terms of what you call the frequency domain representation as well. Now, one particular technique that will become important for us once we start this process is that all these details of nitty-gritty sometimes we would like to hide, and we will simply like to represent the system as a simple block diagram. So, that means that certain input is hitting the system and certain inputs are coming out of it, US creating YS. Just like if I try to look into my last problem, if I say here that the output of the system is in terms of this Tm minus TL or the torque net. So, that is the net torque, and that equals to J theta double dot plus B theta dot. Okay. So, theta dot, if you say that this is the input, that is one way of talking about it. In that case, then I can write down that T bar equals to S square J theta bar S plus B S theta bar, and that means I can write down that theta bar as the input, let us say. So, theta bar equals to T bar over J S square J plus S B. So, I can write down that I have an input which is theta bar, and I have this this transfer function which is 1 over S square J plus S B, and that is related to the output T bar. So, that is the way we can create a block diagram, and that is what I am telling here when I am talking about the transfer function. Sometimes this transfer function could be in two stages, like in last case, if I say no, theta S is not my actual sort of input, but it is the current which is the input, then I have to go one step further by correlating between theta S and the current which was there in the first equation. So, like that we can represent it in terms of more than one transfer functions. Now, the best and the most ideal transfer function block diagram representation is in terms of the closed loop system, which I have earlier described to you, that this, if you remember, that this RS is driving the plant G, and this is the output CS, BS, and the error is driving further the plant. Okay. So, if I try to see the transfer function representation of the whole thing in terms of an equivalent transfer function, then I need to sort of look into this a little more, like I can see what is ES. Okay, ES is nothing but RS minus BS. That is what is ES. Okay, ES equals to RS minus BS. Fine. So, ES is RS minus BS, and that is driving the plant G. So, that means G times RS minus BS, that must be then equal to this output CS. So, this is CS, that is true, but then what is BS? That BS is can be also written as G RS minus, it is CHCS, because CS is the input and H is the transfer function. So, HCS equals to CS. Now, from this, can I get a simplified relationship between CS and RS? Well, let us try. That means you can see here, I can write it as GR minus CGH equals to C. In other words, GR equals to C into 1 plus GH. If I take this term in the other side, in other words, from here I can directly write that CYR is nothing but GY1 plus GH. That is the closed loop transfer function that I am trying to write here. Okay. Now, some of the points important for a block diagram to remember is that only one input and one output will be coming from a block diagram. Okay. And signals may only be summed at explicit summing junction, not like anywhere you try to reduce or increase the signal. And a single signal fed to multiple blocks does not actually imply that we are splitting the signal. It is just that the same signal, that means here also the input is, here also the input is Wi, and here also the input is Wi. Okay. The input splitting does not mean you are taking part of an input. It is just that that pattern of the input is affecting both the transfer function of epsilon and 1 minus epsilon. That is a point we have to keep in mind. There are some more block diagram algebras also, which you will see in any textbook. For example, you have A, B, 2 coming to a junction, then it becomes A minus B, C is coming, it becomes A minus B plus C. Like that, you look at the next one, A and C are plus, B is minus, so it would become A minus B plus C. Like that here, A minus B plus C. So, there are two block diagram representations of it. This one is very, very important, that is A hitting G1 becomes AG1, then G2 becomes AG1 G2, and that means if you do G2 first and G1 later, then also the output is same. So, which means you can alter between G1 and G2 without affecting the output of the system. And here also you can write it equivalently as G1 G2, that would also not alter. And here is a case where G1 and G2 are in the forward part of the loop, and then you can actually take it out and write it as G1 plus G2, because these are summing up here, and if it is minus, then you can break it down. So, you can play with the block diagram algebra. Some are very simple, some are little bit of thought process are required. Okay. This one AG, you are splitting it up, means there are two of them, both are AG, and that also means that you can also write it as here AG and another signal coming up, and AG is the output. So, two outputs are the same between the two cases. Okay. So, like that we can do, like this is a feedback system that we have done, and we already know that a feedback system can be written as G over 1 plus GH, H is G2 here and G is G1. So, it is G1 over 1 plus G1 G2. So, like that, this each one of this case you should be able to basically handle this block diagram algebra by practicing each one of these cases separately. And now then there are advanced block diagrams that you can do with the help of something called Simulink in MATLAB. Okay. So, whatever we are talking about, you can carry it out directly with the help of a Simulink kind of a platform. So, you can try that. There are some concepts which you still do not know, zero poles, etc. I will come to that through the lectures as we will be going through control systems. Okay. Now, let us go to the block diagram for a single degree of freedom system. So, what is that single degree of freedom system? Okay. The system that we are trying to do, the complete block diagram of the system is something like mx double dot, we can see, plus bx dot plus kx equals to FAT, right. So, you can see that FAT is coming here, that is the input, okay, and this FAT equals to what? This FAT, now from the equilibrium point of view, I can write it as FAT minus mx double dot, this is double dot, minus bx dot minus kx equals to 0. So, you can see minus kx is coming here, and then you can see minus bx dot is coming here, and you can see that mx double dot is getting created in the system, okay, but it is 1 by mx double dot. So, the way we are writing it here is that this mx double dot is in the right hand side. So, mx double dot equals to FAT minus bx dot minus kx, or what you can also write is that whatever will be the output coming here. So, x double dot will be 1 over m of this whole thing, FAT minus bx dot minus kx. Now, if you look at it, you see at this point what you are having is actually this part, and then divided by m, that is what you have done, you are going to get the x double dot, and that is the way you can write this equation of motion in the form of a block diagram of a single degree of freedom system. That the same logic then you can actually extend it for different systems. So, one way of doing this, another way, actually this is a block diagram way, Another way of doing this is in terms of signal flow graph. In the signal flow graph, we have vanished these blocks and we have written from this point to this point as two nodes, and the transfer function or the transmittance is written here as Gs. Okay. Like for that closed loop system, it is Gs minus Hs, and here Rs and then unity. That is the way you can write it. So, this is a signal flow graph representation. So, the important thing for a signal flow graph representation is that you need to have a node which is a point representing a variable or signal, then the transmittance that is essentially the same as the gain and or the transfer function, then the branch, how many branches, which is the line segment joining the two nodes, input node, output node. Input node is the source, output node is the sink. There will be some nodes also which are mixed nodes, that means both incoming and outgoing signals will be there, and there will be paths which will be forward path and the cross path, the loop path, that is the signal is fed back. Okay. And then there can be loop gains, that is the product of all the transmittances. There can be two loops which are non-touching, that means they do not share a single common node. No common node is actually non-touching loops, and then a forward path which is a path from an input node to an output node and corresponding gain of it. So, let us look at a signal flow graph representation of a system. So, you can see here that input node is here and this is a mixed node, this is also a mixed node, another input is coming up and then x3 is the output node. Okay. So, signals travel along branches only in the direction of the arrows. Okay. Wherever is the arrow, that is the way the signal goes, and this is a loop. For example, this is a loop. Following this, a signal traveling any branch is multiplied by its transmission, and that becomes the nodal value. At that other end, the value of any node variable is the sum of all signals entering the node, and the value of any node variable is transmitted on all branches leaving out of it. So, some of the basic rules of signal flow graph are that the value of a node with one incoming branch gain A is x2 equals to ax1, okay, where A is the transmittance. Total transmittance of cascaded branch is equal to the product of the branch transmittances, and parallel branches may be combined by adding the transmittances. Mixed node and loops may be eliminated to calculate the complete transfer function. So, for example, x equals to bx2, x2 equals to ax1 plus cx3, so that you can actually gradually eliminate one of these variables, that is this x, and directly represent x2 in terms of x1 and x3. Well, let us see how this can happen. Here you can simply see that x2 output equals to ax1, very simple. Here there is a intermediate node. So, here x3 equals to what? bx2, and that equals to what? x2 equals to what? ax1. So, you can write that x3 equals to abx1. x1 is the input, that is here, and x3 is the output, that is here. Similarly, if you look at this particular problem, here you have x2 coming from two ways, ax1 and bx1. So, you can write it x2 as a plus b, x2 as a plus b x1. And in this case, I can kill this part separately, I can write it as ACBC. Another interesting example is this one, that there is a loop like this between x2 and x3, but I can make it as a self loop. How I can do it? Well, I know that x3 equals to what? x3 equals to bx2, that I already know, and then I also know that what is x2? I know that x2 equals to what? x2 equals to ax1 plus cx3 by definition, right. So, x2 equals to basically ax1 plus cx3. So, it is ax1 plus c b x2. So that is why this x3 is a loop on itself with BC, that is this part of it, and then we can actually do the same thing in terms of the other case also, that is between x3 and x1 I can get the transmittance of the system. So now you see there are various block diagrams and their corresponding signal flow graph. That is what we have given here. Block diagram, signal flow graph. This is just for your practice. You should try to check it. Now, for a complex signal flow graph, of course, it is not so easy to just analyze it. We are going to do something which is called Mason's rule. Okay. So, Mason's rule would require forward path gain, non-touching loop and non-touching loop gain. So, let us see it that the Mason's rule tells us that the final transfer function is actually summation of Ti delta I. Ti's are the ith forward path gain, delta i's are the corresponding gains, and delta is the determinant, which is 1 minus sum of loop gains plus sum of non-touching loop gains taken 2 at a time, then non-touching loop gains 3 at a time with a plus sign, and like that and on it is going to go on. Now then you can try this particular problem where we have given the block diagram, then you can write it in terms of this kind of a signal flow graph. So this is the signal flow graph, and this problem is for what? For a servomotor problem again. Okay. So try the servomotor problem from various directions, and then this signal flow graph that you are getting, you can phase by phase figure out all the transmittances, then what are the non-touching loops there, GL1 and GL2, loop 1 and loop 2 together. Just go back and check yourself that what are the non-touching loops like this loop and this loop. They do not share any common nodes, okay? Whereas this loop share with this particular loop share these nodes common with this this loop, and same thing is true for this. So only two non-touching loop is this one and this one, and that is what we have shown here, that those are the non-touching loops, and then you can actually accordingly figure out what will be the transfer function of the system with the application of the Mason's rule. Now then you can try this particular system, which is a angular position servo, and what will be its signal flow graph. So we have given here the actual system to you, okay, with all the gains and how it is represented as a signal flow graph. So this mathematical abstraction is important for us for the next part of the journey. So you must keep track of it. Now once I assume that you have a complete control over block diagram and signal flow graph, then I come to something which is called how to figure out the dynamic response of a system. For example, the first type of system we look into are the most common systems like a thermocouple, like a potentiometer, or like simple electronic block systems, etc. It is the first order system. There is also another simple example of a first order system. It is called a leaking tank system. This is also a nice mechanical analogy of a first order system. And for this system, what you would see is that these rate of change of the volume inside, okay, and that means if area is constant, it is rate of change of the height of the liquid inside, and which is coming out through a leaky tank, is equivalent to this minus 1 by r h t, and that means you can write it down as a first order differential equation. And then using this relationship, you can actually so this becomes a standard relationship of a first order system, that is something like x dot equals to a x, okay, first order simple system. Now you would see that a low pass RC filter, that would also behave in a very much the same way, that is if V1 is the input and V2 is the output, you would see that ddt of V2 will be 1 over RC V1 minus V2. So it is also a first order relationship of a leaky tank. And what you can see is that typically the response of a first order system, when it is free response, that means you give a kind of a stimulation and then you see the response of the system, you would see that it all depends on this value of a, okay, e to the power atx0. If a is positive, then the response would actually shoot up. So, it will become an unstable solution. If a is less than 0, then what you would see is that it is going to stabilize with respect to time. Okay, it will not shoot up. And depending on whether it is having a large value of negative value of a or small, it is going to take larger time. This is the time. So, faster it will be if the value of a, the magnitude of a will be large. And then that is the free response. What is the forced response of the system? Well, now the first order relationship has an additional part which is plus BUT, and for such a case you can find out the steady state response of the system, which is e to the power at minus t BUT dt, and a typical case can be this type of a system, that is initially 0 and then it is continuing as a unit step signal. For such type of forced response systems, you can actually get the response which would look something like this. Okay. So, you can find it out from this particular governing equation of the system itself by integrating the first order equation. And in case of a ramp input, you can try that, that is ramp is something like a triangular excitation. So, you can try that for a ramp input, this will be a second order with respect to time. And now, once you know all these things, you can create different variations, like if you want to do it for a pulse input, depending on what type of pulse, like if you have a simple pulse like this, then of course, what you can do is that you can have several unit steps working one against the other, and then you can get the response of them, and because it is linear, so a linear combination of them will give you the final response. Now, if I look at a typical example of a thermocouple, this is a thermocouple which is also a first order system, okay, temperature and intelligent temperature control, let us say I want to build up. The governing equation is first order, so tau dy dt plus y equals to kr, and then the solution of it is ys as gsrs. That means I can write it in terms of after Laplace transformation as k 1 by tau s plus 1 by tau. Now, one point you always please keep in mind that the nature of this denominator polynomial determines the order of the system. In this case, the polynomial is of first order. So, this is why it is a first order system. And we can also find out what is the time domain response of the system. So, then given a transfer function to u, you should be able to determine the response of the system corresponding to different type of boundary conditions. For a first order system, you need however only one boundary condition. So, accordingly you can find out what will be the solution of the system. In this case, if the transfer function is given to you and if it is told that determine the response of the system when you are suddenly giving an input stimulus of 100 degree centigrade, then you can actually solve this problem and get the relationship, and then you can get a time domain relationship through the inverse Laplace transformation of the problem. Now, there are various other type of systems. First order system is a very simple system. You can have many times a second order system. So, the difference between first order and the second order is once again that in their transfer function representation, the denominator will now be a second order polynomial, whereas it was first order polynomial for the first case. So, a typical representation of such system could be mass spring viscous damper, or could be an LRC circuit in series or in parallel. Each one of them can give you a corresponding natural frequency of the system. So, the standard form of such second order system will be like either in terms of the time constant, or in terms of the natural frequency, or in terms of the two roots of this second order equation, which we will call as the poles of the equation, or also sometimes we do it in this manner, that is, we keep a real part and an imaginary part of the system. Now, in the next class we will see what are different types of responses of the second order system, and then we will try to implement some controller design through this. Thank you.